Welcome to Building Safety Webinar number 8, Root Cause Analysis. So first of all, disclaimer. The opinions expressed in this presentation of my own do not necessarily represent those of IMechE or any other organisation. Building safety and the development of a safety case process to improve the safety of high-risk buildings is a developing situation and is currently rapid change occurring. So this series of webinars is designed to assist building safety managers and so on who are responsible for safety in high-rise buildings. This is based on the work of the Working Group 1, which was set up by the Competence Steering Group to try to implement recommendations of the Hackett report called the Building a Safer Future. And this working group was led by the Engineering Council and is a collaborative project between different professional engineering institutions and other partners. The objective is to help those involved in the maintenance of a high level of safety in high-risk residential buildings. They should provide an introduction to the topics involved. So root cause analysis, what is it? Well, basically, we need to look below the surface of problems. So you should already have registered your building, submitted your key building information. You probably have already carried out a hazard, and you may have already carried out a bow tie analysis. And all of these help to build up a picture of the kind of systems that you have in your building. But these systems can go wrong. So the first part of root cause analysis is to say, what could go wrong? What if such and such happened? The second part is to look at different kinds of incidents or occurrences and say what went wrong and why. So root cause is about finding the answers to these questions. We need to investigate under the surface to understand possible causes of safety incidents. For example, a key barrier component did not operate as required. Why? Consider individual systems, such as the smoke ventilation system, but also consider possible interactions between systems. This could lead to common cause failure. And consider different scenarios. So the scenario when you have refurbishment going on with perhaps continued residence of people is different from a scenario where everything is tidy and residents are just getting on with their lives in a normal way. You need group team meetings for this work, so probably your hazard team should be reconvened for this. And you need to record and feed the results and actions into the risk assessment and the safety management system. So just for recap really, the structure of a hazard team should include people who know the details of the building, the resident profile of the building, they know about the fire safety and structural safety, they know about other parts of a mixed-use building, for example, there's the retail or offices, or other uses for perhaps the ground floor, the first floor, and the maintenance regimes for the building, also the safety management system and the building safety situation covered by accountable person, and the overview of the maintenance regimes and safety management system being used by other accountable persons in the same building or the same block of buildings. It's useful to have a facilitator and recorder who have expertise and experience of hazard. You may find this difficult to find somebody, but there are a lot of people around who have experience of HAZOP, which is hazard and operability studies. And this process is used a lot in the chemical and process industry, so you may find people there who can help you. So looking at systems, potential problem areas may be associated with purchasing. The original system, was it right for your building anyway? Is it very old now and needs replacing? Can you get spare parts? Is the original supplier still available? The deployment of the system. Is it a system with sensors? Are they in the right place? Has the building layout been modified so perhaps the original deployment's not right? And maintenance and testing. Have you got a third-party original supplier or in-house group looking after this equipment? And what are the regular testing and maintenance parameters? The objective here is that although most systems in your building will be serviced by the manufacturer or suitably qualified third-party contractor, or maybe by an in-house group, the objective of this root cause analysis is not to replace this specialist knowledge, but to gain enough insight to be able to challenge the specialists. In most cases, your reviews of systems should include these external or internal experts. So you may have done a bow tie analysis of your system and you end up with a diagram something like this. So on the left-hand side, you have the preventative barriers, shown in blue here. And on the right-hand side, you have mitigation barriers, which are shown in green. And at the bottom, you have the yellow blocks, which are showing the safety management system looking after these barriers. But is this the whole of your building system? So your building is preventative and mitigation barriers. Each can be thought of as a system, for example, a fire alarm system, but there are other systems in the building like main services. And the building structure itself can also be thought of as a system. So here's another way of looking at systems in your building. This is a diagram of a flat. And the flat, of course, has an external wall. It has a window, VW. It has fire doors, VFD, into the lobby area, the common area, and then again into the stairway. And you may have smoke control systems linking to the common area, maybe directly to the flat. You have instrumentation, utilities, and comms all coming through the walls of the flat and leading to potential problems. So these are all different systems you need to consider. And a possible challenge you may have when looking at root cause analysis is insufficient or poor quality data hampers the identification of root causes. Human bias, we hope, will be taken out by using a team to balance this up. Complexity of the system. In some modern buildings, the systems are very complex and also interdependent, and that could be a difficulty. And a common problem with the root cause analysis is not going beyond the first or obvious issue. So monitoring, some of your systems may have monitoring facilities. For example, your fire alarm system may activate a signal directly to the emergency services and or to named key holders. And some monitored fire alarms can troubleshoot and test themselves to ensure that the system is working correctly. There may also be smoke and heat detectors which have the same facilities. So if you have this type of system, is it working correctly? Can you access the data from your system? So now looking at safety incidents and occurrences. So in the Building Safety Act of 2022, it introduced mandatory reporting of safety occurrences. And this is detailed in the Higher Risk Buildings Management Safety Risk, etc. regulations of 2023. So part 5 of this regulation says safety occurrences means an incident or situation relating to the structural integrity of or spread of fire of a high risk building that meets the risk condition. And then it says the risk condition is met in relation to a part of the building if the use of that part of the building without the incident or situation being remedied would be likely to present a risk of a significant number of deaths or serious injury to a significant number of people. So what this means is safety occurrences not only need to be reported, they must also be investigated and remedied, both to avoid a repeat occurrence and to learn from the experience. A lot can be learnt from incident investigations. Why did it happen? Including near misses. So this is quite a useful diagram from the American Institute of Chemical Engineers. It shows the hazard getting out of control. Then we're waiting for the preventative barriers to take control again. But if they fail, then the mitigation barriers really have the task of preventing any consequences. If they fail, then we have a loss. We may have loss of life, in the worst case, injury, loss of asset, and so on. So the Grenfell Tower disaster, which was a very terrible accident, however, it has left us with some very useful materials which were supported to the Grenfell Tower inquiry. And in particular, Dr. Barbara Lane and her team's reports give an excellent insight into the idea of a sequence for safety of incident. So in this case, the fire spread through the window of the flat of origin of the fire, as described in the Phase 1 report, Section 5. And in Phase 1 report, Appendix J, Dr. Lane describes the smoke extract system requirements and provisions. In this case, smoke extraction is a key mitigation barrier. And these extracts should be read in the context of the total report, which are very interesting. So here's the original system. Was designed to work as a natural ventilation system. It had a fresh air shaft and a smoke extract shaft, serving all the lift lobbies on the residential levels of the building. But there were also supply and extract fans, which could be enabled by the fire brigade to provide additional mechanical ventilation if they consider that to be advantageous. During the refurbishment work of 2012 and 2016, the original system was modified as described in section J5 to provide a combined smoke and climate control system, as you find quite commonly in modern buildings. So these two diagrams are taken from Dr. Lane's report. The left-hand one shows the original system as designed with this is a plan view of the lobby. Shows the fresh air inlet at the bottom of this diagram and the smoke extract at the top, and a big red arrow which shows the smoke coming from a flat with a fire. And on the right shows the modified system. So in this case, in the plan view, we have smoke extract at both the top and bottom of the diagram, and then fresh air coming from the stairs, the common area, to reventilate the lobby. This is just to remind you that in webinar number 5 on smoke control, this shows an actual shaft system. So Dr. Lane's investigations showed that the smoke ventilation system had not operated correctly. So she then asked these 4 questions, which are really very typical root cause questions. So possible reasons for the smoke ventilation system not operating as intended include A, the smoke ventilation system was not correctly commissioned, or B, the smoke ventilation system was not correctly operated by firefighters, C, the smoke ventilation system had one or more defects present immediately before the fire, and D, the smoke ventilation system developed a defect when operated during the fire. So these are very good root cause questions. So now we look at another case study of Lacanau House, which was another terrible fire. I think 6 people died there. This took place 2009, and the fire started on the 9th floor, and then spread very rapidly to the 11th floor, and also spread to the 7th and 5th floor. The real message here is the incredible speed at which the fire spread. So the fire, this is data from Middlesex University. The fire broke out in flat 65 at 16:10 p.m. on the 9th floor. And there was a 999 call at 16:18. And the first appliance arrived at 16:23, which is 5 minutes, which is very quick. But the fire had already spread above flat 79, already spread from flat 65 on the 9th floor up to flat 79 on the 11th floor by 16:24. So within a minute of the fire appliances arriving, the fire had already gone up 2 floors. The fire then spread horizontally along the 11th floor to flat 81. And then also, we think this is due to falling debris from the original fire. This debris probably fell into an open window and started a fire in the 7th floor and similarly in the 5th floor. So the sequence here was, the source of the fire was a faulty television in a flat on the 9th floor. It's thought that the window panels contributed to the spread of fire. So we just look back 1 minute. You can see the window panels are these green parts beneath the windows. So the thinking is that the fire resistance of these window panels was too low and allowed the fire to spread very quickly. The central stairwell, the only way in and out of the building, was quickly filled with thick, dark smoke. So we can see there that whatever smoke extraction system there was, it wasn't effective in keeping this key passageway clear. So there's a report in the Architects Journal and also in Inside Housing. And Brian Coleman, chairman of the London Fire and Emergency Planning Authority, said, in blocks such as this one, you should be safe for an hour before the fire jumps from floor to floor. That wasn't the case in these circumstances. And I think we need to know why the fire spread so quickly. So structural failure is very rare in HRP type buildings, with perhaps the exception of LPS buildings. So I think everybody will be familiar with Ronan Point incident where building suffered partial collapse. You can see in the picture there that one corner of the building has virtually all collapsed. This was due to a gas explosion in one flat. The damage caused was much worse than would have been expected. So after this incident, there was an investigation of the structure by Professor Pugsley, then Professor of Civil Engineering at Bristol University. And he showed that the structure was not strong enough to stand up to the pressure wave from a piped gas explosion or even from a bottle gas explosion. Following that, BRE, the Building Research Establishment, issued a document shown there on the right, which recommends those actions should be taken to investigate these buildings and also the type of strengthening that could be put in to improve the situation. So probably if you have one of these buildings, you've already had a structural survey. If you've not, then you should perhaps be seriously thinking about getting it done quickly because many of them do need attention. Arup has done the structural report on many of these buildings, and at least 3 of their reports are in the public domain. These are ones done for local authorities in London, and they give a very good insight into the problems associated with these buildings. We talk about gas explosions in normal concrete frame buildings, perhaps built to CP3 or later on to Euro code. There seem to be very, very few examples we can find, but this picture here is taken from a paper looking at gas explosions in Poland. And you can see the windows have been blown out in these 2 flats in the middle, both windows and the door. So all glass window, glass door. And what's happened here is really similar to what is intentionally planned in explosion storage buildings, both military and civil actually. And normally there you have a concrete building, but one wall is what's called friable, so it's a very thin material. So if there is an explosion, that wall blows out instantly like a kind of bursting disc. And of course, the building is designed to point away from anything like people or other assets that might be damaged. But the explosion is immediately released into the air and doesn't do any damage. So it looks like in the left-hand picture that the glass windows and door have done exactly as this. They've acted as the friable wall, leaving the concrete structure relatively untouched. Whether this was by design or not, I don't know. If we talk about structural failure of the main structure, then we know that Grenfell Tower after the fire still stands there quite proudly as a good structure. And in Madrid in 2005, Windsor Towers building caught fire and had a terrible fire. It burned for nearly 20 hours, more than 20 hours, I think. But afterwards, the steel structure, this was a steel building, still stood there untouched. So what we have to think about in structural hazards is the building is the hazard, or a part of the building is your hazard. Those are the things that fall on top of people and cause death and injury. Here we're looking at the potential collapse of a HRB building. So on the left is a building in Newburn. Obviously it's not a very tall building, but it shows you the situation very clearly. So here a water from a flood has flowed all around the building and effectively washed away all the infill around the building's supporting columns at the base there. On the right is a picture of the Chaplin Towers in Miami, collapsed in 2021. This was a residential building flat built on the seafront, right near the sea. And it's thought that the collapse was due to corrosion of the basement columns near the seafront. If you look at the picture, you can see on the left-hand side, the remaining bit of building, you can see the car park at the bottom of the building with open column work there, and therefore easily accessible to sea air and corrosion from salt water fumes and air. So if you have a building which is near the seafront, or alternatively is near chemical works where there are corrosive chemical fumes coming off, it's worth having a really good look at the structure. So how often should you inspect your structure? Well, this suggested practice is based on work that John Carpenter and others did for looking at car park structures. It divides buildings into two types, category A and category B. Category A is a building which is designed to code. So on the fire side, perhaps CP3 or B7974, or structurally it's a Eurocode building. And category B is a building which is not designed to any current structure code or anything we know about, probably older buildings. And the suggestion is that category A buildings should be routinely inspected every 2 years, and then a condition survey every 6 years, and a structural survey depending upon the outcome of the condition survey. And category B buildings need a condition survey every 2 years, but then a structural survey according to condition again. So a category B building, which might be a pre-war building, for example, should be surveyed every 2 years, and the structural surveys according to condition. So this is just a suggested practice. It's what was recommended for car parks, and I think it perhaps can be applied to HRB type buildings as well. So thank you very much. That's the end of this webinar. There's my contact details if you want them, and I look forward to hearing from anybody if they want to have some more information. So now stop sharing, and stop presenting, and also we'll stop the recording here.